Welcome to Introduction to Optimization, Tutorial 3, Convex Sets and Functions. A set C is called convex if for any x and y in C and lambda in the range of 0 and 1, lambda x plus minus 1 minus lambda y is also in C. A convex function is a function f from C to R defined over a convex set C that for every x and y in C and lambda in between 0 and 1, f of lambda x plus 1 minus lambda y is smaller than lambda f of x plus 1 minus lambda f of y. The geometrical interpretation of that meaning, a convex set, meaning that if you stretch a line between x and y, every point on the line would be in the set as well. But in a non-convex set, there are some x and y in the set that if you stretch a line between them, there would be points that are not in the set. A convex function is if you stretch a line between x and y, 2 points on the function, every point on the function between x and y would be below that line. A concave function is the opposite of a convex function because every point of the function between x and y is larger than the line that is drawn between the two. The gradient inequality states that if f is a convex function and continuously differentiable defined over a convex set C, then f of x plus the gradient of f at point x transpose multiplied by y minus x is smaller or equal to f of y. You can get the intuition for that by seeing that the left side of the inequality is the first order Taylor expansion of f of x. You can see that the geometric interpretation is as defined over here.
Proof of the gradient inequality. Let f be a convex function, and so by the definition we can infer this inequality. Now we will subtract f of x from both sides and divide by lambda. Inside the left side of the inequality, let's change the way it's written and we would get this. Now let's see what happens when lambda approaches 0. If we replace lambda multiplied by y minus x with epsilon, we will get that this limit is equal to this limit. We just replace this expression with epsilon. So let's move this to a multiplication, and we get this limit. Now this limit is the definition of the derivative, and this is y minus x. And so we got that this limit is actually equal to f tag x multiplied by y minus x. And now we got this inequality. Now let's define the function g. While f is a function from Rn to R, g will be a function from R to R. And because f is convex, g is also convex, because g gets the values across f on the line connecting x and y, and because f is convex, so will be g. Using the chain rule of derivatives, we know that the derivative of g at point x is as follows. And so, using that we have shown in the last slide about one-dimensional convex function, we know that g of 1 is larger or equal to g0 plus the derivative at g tag 0. Now let's plug in the expression for g and g tag. So we know that f of y is larger or equal to f of x plus the gradient of f of x multiplied by y minus x, and this is the gradient inequality. Jensen's inequality is an extension of the definition of a convex function. It states that for every linear combination with coefficients that sums up to 1 is smaller than the same linear combination but with f applied before the summation. The intuition of why it is true is applying the definition of convex functions again and again. If f is a convex function, then its second derivative, the Hessian matrix, has to be positive semi-definite at every point in the domain of the function. Optimality conditions for minimum. If the function is convex, then the gradient being 0 is sufficient. If not, then at the optimal point, the Hessian needs to be positive semi-definite as well. Question number 1. Let Ci in Rn be a convex set of any I in big I, where big I is an index set, possibly infinite. Prove that the intersection C, that is the intersection of all the Ci's, is a convex set. Before viewing the solution, I advise you to try and solve the question yourselves. The solution is, for any x and y in C, we know that for every I, x and y is also in Ci, by the definition of C, because C is the intersection of all the Ci's. And because Ci is a convex set, so for every lambda between 0 and 1, lambda x plus 1 minus lambda y is also in Ci. Because that is true for every I, that is meaning that lambda x plus 1 minus lambda y is also in C. Because if it's in every Ci, then it is also in the intersection of all the Ci's being C, and that is the very definition of the intersection. And so, because it holds the convexity conditions, we know that C is a convex set. Let C be a convex set, and let A be a matrix that is not necessarily invertible. We define that A inverse C is all the x's in Rn that Ax are in C. Let's prove that A inverse C is convex. So basically, for a matrix A that is not necessarily invertible, we define this set. This set contains all the vector x that are in Rm space, and if we multiply them from the left with A, they would be in C. I encourage you to pause the video right now and try to solve it yourself before viewing the solution. For any x and y in the set and lambda between 0 and 1, we know that Ax and Ay are in C. And because C is a convex set, we know that lambda Ax plus 1 minus lambda Ay is in C. So if we change the order of summation and multiplication, we see that this expression could be written as A multiplied by lambda x plus 1 minus lambda y. Hence, by the definition, lambda x plus 1 minus lambda y is in the inverse of C, because A multiplied by this vector is in C, and this is the way that we defined this set. And so, because for every x and y in the set, and for every lambda between 0 and 1, we have this condition, then we know that this set. Question 3. Let C be a convex set. Let's define the function delta to be the following function: 0 on x that is in C, and infinity on x that is not in C. Let's prove that lambda is a convex function by assuming that infinity is smaller or equal to infinity. I encourage you to prove that yourself before viewing my solution. The solution is, for every x and y and r and lambda between 0 and 1, delta of lambda x plus 1 minus lambda y is 0 if this expression is in C, and infinity if this expression is not in C. So if lambda is equal to 0 or 1, we will get the convexity conditions to require that delta x is smaller or equal than delta x, or delta y is smaller or equal than delta y, and that will always hold. So we're only interested if lambda is not 0 or 1. So if x and y are in C, because C is a convex set, then lambda x plus 1 minus lambda y is in C as well. That is meaning that delta of this expression is 0. And so if delta of this expression is 0, it is indeed smaller or equal than this expression, because delta of x and delta of y are 0 as well, because x and y are in C. And so 0 is smaller or equal than 0, and the conditions to convexity are held. And so if x or y is not in C, because we required that lambda is not 0 or 1, one of these is infinity, and so this entire expression is infinity, and none of these is 0, because we know that lambda is not 0 or 1. And so for every value of lambda x plus 1 minus lambda y, we know that delta of lambda x plus 1 minus lambda y will be smaller or equal to this expression, because it is 0 or infinity, and this is infinity, and so we know that this part will always be bigger than this part, because this is infinity, and this could be 0 or infinity. Question number 4. Let f be a convex function defined over the convex set C. Let's prove that for any alpha, the level set given by the all the x's in C that f of x is smaller or equal to alpha is a convex set. I encourage you to try to solve it yourself before viewing the solution. Remember, f is a convex function and C is a convex set. The proof is as follows. Given any x and y in the level set and lambda between 0 and 1, we have that f of lambda x plus 1 minus lambda y is smaller or equal to lambda f of x plus 1 minus lambda f of y because f is a convex function. And because this is in the level set, we know that these f of x and f of y are smaller or equal to alpha. So this is smaller or equal than lambda alpha plus 1 minus lambda alpha, and that is alpha. And so, therefore, lambda x plus 1 minus lambda y is in the level set. Question number 5. Let f of 1 till fk be k functions from C to R. Those functions are convex and C is a convex set. We define f of x to be the pointwise maximum over all of the fi's, meaning that f of x at point x is the maximum over fix for every I. Let's prove that f of x is a convex function. I encourage you to do it yourself and then view the solution. The proof is as follows. For every x and y in C and lambda between 0 and 1, we have that for every I between 1 and k, fi of lambda x plus 1 minus lambda y is smaller or equal to lambda fi of x plus 1 minus lambda fi of y. That is because all of these functions are convex. By applying the max operator on both sides of the inequality, we get that if we put max over here, we get the definition of f, and so f of lambda x plus 1 minus lambda y is equal to the maximum over all the i's of this expression. That is smaller or equal than the maximum of lambda fix plus 1 minus lambda fi of y. That is true because of fi being a convex function. That is smaller or equal to the maximum of lambda fi of x plus the maximum 1 minus lambda fi of y. And that is equal to lambda over the maximum and 1 minus lambda over the maximum, meaning we took lambda and 1 minus lambda out of the maximum. Why did we do that? Because this is the definition of f and this is the definition of f. And so we got lambda f of x plus 1 minus lambda f of y, and that is exactly the definition of f and a convex function. So let f be a continuously differentiable function over a convex set C, and f also would be a convex function over C. So let's introduce this lemma. So the gradient of f of x minus the gradient of f of y transpose multiplied by x minus y is larger or equal to 0 for every x and y in C. Let's prove this theorem. I encourage you to try to solve it yourself before viewing this. The proof is as follows. By using the gradient inequality we have seen before for both sides, once at point x in relation to y and once in reverse, we get those two expressions. Then summing the results and flipping the sign of one of the gradients to change the order of subtraction, we get what we wanted. We also cancel out the f of x and f of y from both sides. Flipping this to x minus y and taking the minus out over here, we get the gradient of f of y minus the gradient of f of x transpose multiplied by x minus y. So now, we change the order of subtraction here and flip the sign because we multiplied it by minus 1, and we get exactly the lemma that we